start with section 17.1, Green's theorem. It's the first of the three theorems of vector calc, when the three final theorems of vector calculus. So let's first talk about closed curves and contour integrals, and just do a few notations to make the explanation of the theorem easier. Let C be a curve parameterized by R on the domain AB, and C is closed if R begins and ends at the same point. That is, R of A equal to R of B. We've seen this one before. C is simple, so the curve C is simple if it doesn't intersect itself. And that makes R a one-to-one function. And then a line integral around the closed curve C is called contour integral, and that the round thing over the integral symbol, that means the contour integral. And so we show them either with FDS, which is the scalar line integral, or f dot dr over the contour, and a contour integral of f dot dr, which is the vector line integral. And so those are the notations again. Again, this was a discussion that we had in 15.3, the contour integral of, 16.3, and contour integral of f dot dr is equal to 0 if f is conservative. And when f is conservative, then it's path independent, and then the contour integral or integral over any closed path is going to be 0. So these are the stuff that we know. Let's show you a few pictures. So the one on top is the closed. It's simple but not closed. This one is neither simple nor closed. That one is not simple, but it's closed. It's going back itself. So this one is a simple and closed curve, basically, the one that I drew over there. Every simple closed curve in R2 is boundary of some region D. We write C equal to that partial thing over here, means boundary of D. We have, when we talk about the boundary of D, we usually have either clockwise or counterclockwise direction to go. And if it's not mentioned, then it's going to be counterclockwise. That's the standard parameterization of the unit circle, and we go with counterclockwise. And so this clockwise or counterclockwise tells you whether or not, if you're walking on that path, whether or not the region is going to be on your left or your right. So for counterclockwise, it's going to be on your left. For clockwise, it's going to be on your right. So let's do some examples of contour integrals. Let C be a circle of radius r with the standard parameterization. What's the standard parameterization of C? That is r cosine of t and r sine of t, right? And so another thing that I want to say is this is going to be x of t. This one is y of t. Now, computing integral, contour integral over C of x dy means that you're computing r cosine of t, and dy is going to be y prime times dt, and y prime is r cosine of t dt. that is when one full round is integral from 0 to 2 pi r squared cosine squared t dt, which if you compute, you will end up with pi r squared. Okay, so the next thing to notice is find the integral y dx, and that is, again, y is r sine t, and dx is derivative of x, which is our derivative of r cosine t dt, and you compute. And you get negative pi r squared this time. If you add the two together, you end up to have 0, where one is the negative of the other. Now notice, when you're saying contour integral of x dy and contour integral of y dx, you basically, what you did here is you calculated the integral, again, this plus that, these two added together is going to be the integral of y and x dot dr. And so now y and x dot dr is basically the gradient of function f of xy equal to xy. Therefore, this line integral is going to be 0, and the two of those are going to be equal to each other. We're going to come back to this little fact after we discuss the theorem itself as well. Another example of contour integrals. Let D be the region AB cross CD. That's that rectangle right there. And let C be made the boundary of the region, which is made of 3 pieces. The bottom part is S, the right side is E, and then N, and then W. You notice that I'm going from counterclockwise, right? And then note that basically dy dt over the S is going to be 0, also on N. Dx dt is going to be 0 on E and on WY, because S and N, Y is not changing, and in E and W, X is not changing. And so that's something to remember. Then we want to find the integral x dy over the union of all those 4 pieces. And so I will have the, when I have the s dy, since basically dy is equal to 0 on the region S and N, I can completely ignore those because those are going to be 2 zero integrals in there, and just find the integral on the E and W. Integral over E and starts at basically, now at this point I want to parameterize x, and x at E is equal to B. X for E right there is B. So I put B in there, and then Y runs from C to D. So C to D. Over here, X is A, and then Y runs from D to C. And computing that, you get for the first integral, you get D minus C times B. For the second integral, you get D minus C times A. I'm sorry, negative D minus C times a. And then when you factor d minus c, you get d minus c times v minus a, which is exactly the area of the rectangle. Similarly, if you want to find the contour integral of y dx, you end up with the fact since dx is 0 on E and W, you're just computing the integral over n and s, and you end up with negative area of d basically, and that's something we just did with then we figured out the contour integral x dy was negative contour integral y dx in the previous example. So this is going to give you an insight on the theorem that we're going to discuss in the next video.